Integrated one. Made these during coronavirus, not that anybody cares, 2020. And started with the end chapters first. Then I went back and did some middle chapters for some kids that had missed some school during the year. And then I started chapter 1 and worked through chapter 4, and this is the last one. So if you're watching this video, sorry for wasting 20 to 30 seconds of your life if you listen to this, but I am excited to be done. So interpreting correlation in context. Although the correlation coefficient is widely used to describe the amount of scatter in a linear association, it is unfortunate arbitrary computation. Correlation does not have a real-world meaning. If I say R of 0.2, it means nothing. In this lesson, you will learn a way to make sense in context of the correlation coefficient. So, in lesson 413, Karen discovered that a human's height is associated with their forearm length. Karen is curious whether height is also associated with foot size. So it was not practical for Karen to measure her classmates' feet, so she collected the following shoe size data from her classmates. Read the math notes in this lesson, then use the definition of R squared and the data below to write a sentence about the variation in height of Karen's class. So first we'll run down and read what R squared is. So it says the value of the correlation coefficient squared does have a real world meaning. So we're literally going to square whatever R is, we multiply it by itself to get R squared. The correlation coefficient squared is written as R squared and expressed as a percent. So correlation coefficient squared, or R squared, we put as a percent. Even though the calculator gives it to us as a decimal, we're going to change it into a percent. Its meaning is that R squared percentage of the variability in the dependent variable can be explained by a linear relationship with the independent variable. The way I say it is output is associated with input. So 72% of the output is associated with the input. It's not, like we learned in 423, it's not caused by it, but they are associated together. Well, it might be caused by it. We don't know if it's caused by it, but we do know there's an association. So for example, if the association between the number of fertilizer and plant height has a correlation coefficient of 0.6, then R squared would be 0.6 times 0.6 would be 0.36, but we don't write it as a decimal, we write it as a percent. So we can say 36% of the variability in plant height can be explained by a linear relationship with the amount of fertilizer used. Or I would say 36% of plant height is associated with the amount of fertilizer used. That's just how I prefer to say it. Again, it's not caused by, it's associated with. So the rest of the variation in plant height is explained by other variables, the amount of water, sunlight, soil type, whatever. The correlation coefficient, along with the interpretation of R squared, is used to describe the strength of the linear association. So we're going to use that as we kind of go through. So first of all, a couple things here about the shoe size. First of all, this person has a shoe size of 8.4, which makes no sense. Although when you look at the checksum, it's 198.9, so the book meant to put in 0.4 instead of 0.5, which I don't understand. The other thing is you'll notice this column and this column go together. So columns 1 and 3 add up to this, and columns 2 and 4 add up to this. However, when I put these in the calculator, I'm not going to make them columns 1 and 3. So I'll go 712, clear this out. First thing I'm going to do is I'm actually going to turn the catalog on so I don't forget. So remember, I need to go diagnostics on, but if I'm going to talk about R and R squared, it's really easy to forget to turn my diagnostics on. And again, they're not on until this says done. So when I go in here and I go to put my data in, again, I'm going to go down the whole column 1, but instead of making another column, now it just jumps to here. And at that point, I'll pause and put the rest of the data in. Again, it looks like 4 columns, but it's just 2. I put all that data in. I have the same column length, so I feel like I'm ready for my checksum. I will go stat, calc, 2 variable stats, and I will run that on calculate and hope that I have the right amount. So 198.9 is correct. 4070 is correct. So happy with that. Now I'm just going to go through the whole process. So first thing I'll do is I will run the LSRL, and again I will save this under vars, yvars, function 1, and I'll run this thing. And I'm going to ignore this stuff for now, and I'm going to focus on the equation. So I have y equals, actually I guess I can do the whole thing, 3.97x plus 131. What does that mean? That means I have 3.97 y's, or centimeters of height, for every one shoe size. So if your shoe size goes up 1, your height goes up 3.97 centimeters. And if I have no shoe size, or a shoe size of 0, I have a height of 131 centimeters. My R is 0.86, which is positive and strong. And my R squared, again, this is a percent. 74% of the height is associated with the shoe size. So there's 26% associated with other things. Maybe, I don't know, maybe diet or maybe age, right? Sometimes you see some kids with some giant feet and hands, but they haven't quite grown into their body yet. So, you know, maybe it's a 14-year-old kid that's going to grow 6 inches, but his feet aren't going to get any bigger. Long story short, again, we should be able to make sense of the slope and y-intercept in context. We should understand what the R is saying. Again, positive and strong, and the R squared, 74% of the output, or the height in centimeters, associated with the shoe size, or explained with a linear relationship with the shoe size. I'm not done though. I do want to go ahead and see what this looks like. Again, it's positive and strong, so I do expect it to look that way. And you can see positive and strong. It looks pretty good. The next thing I will do is I'll run my residual plot, because again, the R and R squared don't even necessarily mean anything if, what am I doing real quick? Okay. I'm sorry. I'm like, let's go here. My R and R squared don't even necessarily mean anything if it's not aligned to begin with. So we'll go second list. Apologize there. I was doing something else in my brain. So I will go to my stat plot. I will plot L1, L3. And again, what I'm looking for is no pattern. If I don't see a pattern, then I feel like a line is a good fit. So we'll see here. And I definitely don't see a pattern, so I definitely think a line is a good fit. Having done all that, let's go ahead and set this thing up and do it in Desmos again. When I go to Desmos, I'm going to go ahead and first of all put a graph in, or a table in, and then I need to go ahead and transfer this data into that table. So again, I'm just going to do L1, L2. The book will take care, I'm sorry, Desmos will take care of L3 for me. I'm going to pause while I do that. And I'm going to kind of go back and look at the data. Obviously the scale's big here, so it looks kind of funky. You know, my scale's definitely a little bit kind of weird there. I will go ahead and I will get the line of best fit. So y1, y1 tilde mx1 plus b. Hoping I get the same one I did at the calculator, so 3.97x plus 131. So looks good. My slope and y-intercept look the same. My R squared looked the same. So pretty good here. Pretty pleased. Again, 0.86 R tells me it's positive and strong. This is again a percent. 74% of the output, or of the height in centimeters, is associated with the shoe size. So every time my shoe size grows 1, my height grows 3.97 centimeters. And again, if I want to plot, you can see it plots all the residuals, but I just have to go down to where it is and look at the residual plot. And it looks pretty good right there. Nothing too crazy, like we said over here. The residual plot definitely kind of tells us that it's scattered and that there is no pattern, so a line is a good fit. So this R and R squared are actually beneficial to use. All right. It says if only a portion of the variability in height can be explained by shoe size, what other factors might be? And like we already talked about those, maybe diet, maybe age. Again, a lot of times teenagers have giant hands and feet, but they haven't quite grown yet. So suppose Alice, I don't know, collected the following data for 5 random students in her class. So we're going to run all this data all over again. So let me pause this and set this up in Desmos and in my calculator. Before I forget, I will turn my catalog on. So diagnostics. I should turn my diagnostics on using the catalog. All right, so I think I showed already that I have my data here, but maybe I didn't. I put that data in. I will go stat, calc, linear regression. Again, I will go vars, y vars to save it so I don't have to type it in myself. And I will calculate. So what this tells me, my slope is 4, so my height goes up 4 centimeters for every one shoe size. If I had a shoe size of 0, I'd be 130 centimeters tall. My R is 1. That means that it is positive and a perfect association. And that means 100% of my height is associated with shoe size. So again, but I only have 5 pieces of data. But again, if you, according to this data and this prediction line, if you give me someone's shoe size, I can tell you exactly how tall they are with no doubt. That's what these mean. So let's go ahead and turn on our stat plot and kind of see what it is that we're talking about. So I will look here and go graph zoom 9, and you can see it goes straight through the points. Again, if I run my residuals, second list, 7, 1, so second list, I don't know what happened there, but I did something. Hit enter. All my residuals are 0, which is not surprising. I will go to my stat plot and I will run L1, L3. And when I say it's not surprising, it's because this hit every single point, right? My prediction and my actual was exactly the same, so there would be no residual. I'll go zoom 9, and it says quit range. It doesn't like what's going on with the window. It's real confused by what's happening here because we have no real thing going on here, right? So the calculator's sort of freaking out at me. So I'll change my Y minimum and my Y maximum off of 0 and graph it, and you can see, there we go. We have exactly a line where there is no residual. Again, I went to window and had to change my Y scale just because it kind of freaked the calculator out. If I go here, I have the data in, you can see I have my R squared, same slope, everything. And again, you can see my line of best fit goes through. If I plot my residuals, again, down here, you can see there's really nothing to see as there is no residuals. So it says, what is the correlation coefficient? Why is this data unusual? Because it's perfect, right? I can perfectly predict someone's height based on their shoe size. In the context of this problem, what does the correlation coefficient tell Elise or Alice about the association between the height? Well, there's a perfect association. 100% of the height is associated with shoe size. What can Alice say about the variability in the height in her unusual class? What can she say about predicting the height for a student? So very little variability to none, and she can make a perfect prediction. All right, so Holly created a scatter plot showing it right for girls in her class. So it looks like this. Again, this is a scatter plot. Here's the score on the Chapter 5 test, and here's how tall you are. What do you notice about the pattern? Well, there really is no pattern. So I would say the R is 0, and that would make sense because there's no reason to think that the score on the test has anything to do with your height. There's no reason to think a tall person would do better or worse on the Chapter 5 test. So again, I would say the R is 0, and 0% of the height is associated with the score on the test, right? They just don't make sense to go together. It says the best prediction Holly can make is that a girl has average height no matter what her test score was. Holly calculated the average height of the girls in her class of 162 centimeters. What would the line of best fit look like? Again, we would just go side to side at 162. So y equals 162, and it would be a flat line. Excuse me 1 second. I apologize. So the reason it'd be y equals 162 is the average is 162, right? So that's where the horizontal line y equals 162 would go, and it would have an R of 0. That's why it would be flat. All right. So wrapping up, getting close to the end of Integrated 1 book. So excited. So when Julia went around town on problem 449 comparing prices of the pizzas, she gathered this data. So what's the LSRL? Interpret, blah, blah, blah. So again, I'm going to go to my calculator. Again, I am going to clear the memory. And again, I'm going to kind of run all of this data. So I'm going to input here. Actually, it shouldn't take very long. I guess I don't mind wasting, what, 20 of your seconds if you're actually watching this. Okay, so we have that data. Again, I'm going to turn my catalog on. I will go to diagnostics. I'm sorry, I will turn my diagnostics on using my catalog. Again, when I hit enter, it's not on. I hit enter again, now it is on. I will run my LSRL. I will go to vars, y vars, function y1. I get the equation. And we had talked about this, $1.36 in a previous video. We had talked about this. So 1.36 y's or dollars, right? $1.36 for every 1x for every topping. $1.36 per topping, $7.74 for no topping pizza. My R is positive and strong, and 74% of the price is associated with the number of toppings. And again, what are the other 26%? The other 26 is probably things like how fancy it is, if it's on sale, the ingredients they use, those kinds of things. So we figured out the LSRL, we interpreted the y-intercept in context, was a correlation coefficient R and R squared. We said what that is. So one thing we didn't do is a residual plot, so let's go ahead and do the residual plot. Even if it doesn't ask for that, I still think it's a good thing to make sure that we know how to do for the test, etc. So I will go here. Second, I keep doing that. I don't know if what am I missing or something? I don't know. So second list 7, enter, and I will go here. And again, I'm just checking to see if I notice a pattern in my residual plot, so I can determine if I even think a line is a good fit. So we'll go graph and zoom 9, and you can see I think a line's a good fit, kind of up, down. So yeah, I don't see a pattern. I'll say a line is a good fit. So in problem 449, you wrote a report describing this association. Now improve upon the report by making it more mathematically precise and quantitative. Use the slope when describing direction, which we've already done. Use a sentence about R squared when describing strength, which again we've already done. And we actually threw in extra that it was that a line is a good fit as well. So I'm gonna run over here and do the same thing in Desmos just so you can see it, and we'll leave it at that. Actually, you know, I can just leave the y equals mx plus b in here, and what I can do is just delete all of this data. Just kind of show you a shortcut if you're already using Desmos. Kind of not a bad idea to do this. Again, I already have all this stuff here, so I can just go ahead and put my data in here. So it's 1, 3, 4, 6, 3, 5, 0. Again, I apologize for making you kind of suffer through this, but I just think it's interesting to see how you can sort of save time once you already have Desmos set up. So the last ones were 2, 9. You can see I already have all this data in here, right? I already have, there's my slope, my y-intercept, my r and r squared. It does confirm. I'm actually already graphing my line of best fit. So there you go. There's my line of best fits. Again, I can take that out if I want. And then there's my residual plot. And again, you can see there's no pattern there as well. All right, so finally, it says Julia's father. Last question of integrated 1. I could cry. I'm so excited. Julia's father finally opened his pizza parlor. He charges $7 for a cheese pizza, plus $1.50 for each additional topping. Choose 4 or 5 points and make a scatter plot of the prices of pizza versus the number of toppings at his pizza parlor. So let's just go ahead and, I'm just gonna, rather than go through a bunch of trouble on this, I'm just going to put this in because I think it'll be pretty easy to do. So it's saying, and I hope you see where this is already going, but I'll go 0, 1, 2, 3, 4. It says 4 or 5 points. That'll be 5 points. It was $7. Then he's going to add $1.50 each. So, if he adds $1.50, that'll be $8.50. This will be 9, 10. This would be $11.50, and this would be $13. So you can see 0 toppings $7, 1 topping $8.50, 2 toppings $10, 3 $11.50, 4 $13. I hope you see where this is going because it's going in a very obvious place. So if I run all this data, again, I'll turn my diagnostics on. So I will run my LSRL. I will save it and revise YVARs. I get the equation. Y equals 1.5x plus 7, which makes sense because if you think about it, the data I put exactly hit that. My R and R squared, 1 positive association and perfect association. 100% of the price is associated with the number of toppings because that's literally how he chose his menu. If we go ahead and graph this, we will see that that actually is the case and that it hits each point exactly, right? Which is no surprise. We're going to go and we're going to run the residuals. We expect all our residuals to be 0 because again, we chose this data to be perfect. And when I run this, my calculator will freak out because I have no residuals, and I will have to go into my window and change the window a little bit because you'll see the minimum and maximum is 0, so that kind of makes the calculator a little bit confused. So I'll make my Y minimum -1 and my I don't know what I did there. I'll make my Y minimum -1 and my Y why is this not? Oh, I'm using a minus. I'm not using a negative. The calculator makes you use a negative. My mistake. And my Y maximum is 1. I'll graph, and you can see that's what it looks like. And again, if I go into Desmos and I have all the same data, so I can close this and open a new table. You'll notice though it says X2, but this goes to Y1 and X1, so I'm just going to go change these ones so that they're 1, so that it does reference my equation. So again, I have 0, 7, 1 was 850, 2 was 10, 3 was 1150, 4 was 13. And again, you can see perfect correlation. Y equals 1.5x plus 7, positive and strong. 100% of output is associated with input. And my plot is perfect. So I kind of ran through that last one, but again, we expected to see that. So what is R squared? We talked about. Write a sentence. We don't need to. We are 100% done with the Integrated 1 book. So excited. Have a good one. Reach out if you have questions.